I'm just going to do a quick check if you can hear me. Yes, you can hear me. Cool, amazing. So welcome, everyone. Thanks for attending this session. My name is Semjen, and I'm going to talk about Kafka generating value in retail with Confluent. So it's a very in medias res presentation because I thought I would start with all the use cases we often see when we talk to retail clients. So the very first one is inventory management. So very often, if you have an online store, you have a physical store as well. Sometimes when your customers order a product, they might want to pick it up from the physical store, and you just need to make sure that that item is actually in stock. And unfortunately, sometimes those items get removed without anyone having paid for them. So you might want to account for those scenarios when someone may commit a theft in your store, so you don't have anything in stock that your customers ordered. Very often, people are trying to enhance customer experience. These scenarios would include, for example, tracking a shipment or alerting your customers when your package will arrive. It's all real time. Every time a package gets to another distribution center, you would get a message about when your package is likely to be delivered. And it just creates a lot better customer experience because you can prepare when you're going to receive that package, when the product is going to be with you. So forecasting and machine learning use cases. These have become popular recently, and we support quite a lot of these use cases. So when you browse a website, you click around, you have your product choices, you may have shopped around in a web shop, and you may also have a loyalty card. So we can collect all sort of omni-channel data about how you interact with customers, and maybe we can forecast what product you're likely to buy next. So this is also something that we very often see retailer customers want to use real-time software for. And the last one, and this is the one I'm going to talk a lot about today in this presentation, is to reduce the total cost of ownership and to remove the technical debt that you may have as a long-established, let's say 30, 40-year-old organization. So very often when we get these queries, one of the main themes we see is that we would like to move into the cloud, or we may not have chosen the right cloud provider and we would want to migrate in between clouds. There are all sorts of scenarios that will require a bit of integration or to build data pipelines to modernize an existing system. So this is usually where we start from, the monolith. And I'm not sure how many of you have worked with Monolith. I started my career in the financial industry, so we had a huge monolithic system. And we tried to update tables, and we tried to add new columns, and we tried to evolve the system, and it was just extremely difficult because you just couldn't do integration testing on a huge repo that you have on GitHub. It's just impossible to do. So what we started doing, which is a really bad practice, do not do this, is that we started reusing columns for different purposes. So when it said price, 99% of the cases it was the price, but for some other assets it may have been something else. It was like an index level or something like that. So people made these really bad architectural choices because they couldn't really create a new database or a new microservice or something that could migrate them from this traditional approach. So it was difficult. We relied heavily on each other. And what was even worse is that, people leave the organization, these processes become undocumented, and then you just don't even know what's going on in your database. You have to write 400 lines of SQL code to actually extract something out of the system. And there's an element people don't talk a lot about, which is when you hire someone and you want them to be efficient and you want them to produce value on day one, it's very difficult with this monolithic system because you expect them to upskill on the whole system itself. It's not just a single functionality they will be responsible for, but it's the whole system they need to integrate with. It's the whole functionality they need to understand in order to update the system. So it's long development cycles, it's expensive from a people perspective as well, and it's quite unreliable. So people started to realize this, and we started adopting to microservices. And the microservice approach is a lot better because now you have single functionalities wrapped into a package, and what you need to do is you can give the developers autonomy to work on what they want to. You can choose your language, you can choose your choice of database, because all you have to do is create that microservice responsible for a single functionality, and then what you're probably responsible for, and this is where the difficult part comes in, is orchestration. It's like how you call them, how you scale them, how much do you need to wait for them, how many performance issues you may have with them. So it's not a solution for everything, but it does the job in pretty well, like a lot better than in the monolithic use cases. So there are two approaches that became really popular in between inter-service communications. And one of them is the REST APIs, and the second one is messaging queues. I will dwell into both of them in a bit. So REST APIs, they're amazing. They have been around for a while. They are widely used for web communications. And I think the key thing here, that they are synchronous. So every time you send a request, you wait for a response. So every time you want to design a system with REST, you want to make sure you're using it in a case where you require synchronous communication. So there are a few things mentioned around REST APIs. They are slow. I don't really like this term, to be honest, because they are slow compared to a function call in code, yes, but they are not that slow in reality. But they are not designed to scale really well. I mean, it becomes difficult to scale them, and especially if you have many services calling each other, and you might end up with a bottleneck that may impact your whole module's performance. You may need to scale down your other services so you don't flood your REST APIs with too many messages. So there are a number of things to think about, and maybe the last one I will mention is there isn't a very stable data contract about what you're going to get out of the REST API. It will throw you a response that you can work with if it does respond to you. But if you need to do error handling and you need to do all sort of things, then you replicate this error handling and business logic every time a new organizational unit calls your REST API. So it's a bit cumbersome. It does take a bit of time to use them, but they're useful and they have their place to use them. All I'm saying is designing a very REST-based API approach may not lead to the best results if this is the only pattern that you use. And then we are moving on to messaging queues. So they were established in the 90s, and they are able to solve actually some of the elasticity problems around the REST APIs. For example, if you put all your messages into a queue before just sending it right to the REST API or to a REST service, you can make sure that it only gets picked up once the service actually can respond. So it does solve elasticity issues. It's a pub/sub messaging system, and yes, you can use this for asynchronous communication. And it's been used for asynchronous communication for quite a while. For example, IBM MQ, RabbitMQ, and they started to build better tooling around them. But I would say it's still limited how much governance you can put around these queues. Also, what's interesting about them is it's very much like a broadcasting architecture. So in case you've got a message in the queue and you've got a number of clients subscribing to that, and for whatever reason your application is down and it's not an active listener on that queue, that message is gone after the second everyone received it who was an active subscriber. So there's no persistence, there's no way you can go back in time, and that may be difficult. Like in some scenarios, your systems didn't work for whatever reason correctly, and you just want to go back in time and you want to check like what may have gone wrong. With MQ, that's a pretty difficult task to do. You might need to design the system in order to be ready for that. So what do we do in retail? Again, so maybe there is a sale, a shipment, a customer click, or a stock refill. There are a number of events happening in the organization, and the data is continuously evolving, it's continuously updating, and lands in Confluent. And I'm going to talk about like why this is so different from the traditional approach we think about data development and building architecture. But in reality, this approach enables you to react to events happening in your organization in real time. So why is that amazing? So when I started my career as a developer, the way development worked was we had a business team, and they had a process. For example, you have to pay taxes on a product that was just sold in your online shop. And that process had multiple steps. It's like a customer made an order, then I need to report it, and then I need to calculate it with a percentage. So you had the process in mind, and always like in a procedure or in a single functionality, you would code that process, you would own that process as a development team, and you would own the process from the start to the end. Here it's a very different approach, and to be honest, when I started with this, it does feel a little uncomfortable first to code this way, because this is not what you expect, this is not what you're used to, and this is not how our brains usually work when you learn how to code. So in this scenario, you've got an order created, and that's an event. And it's an event for the whole organization, for every single unit. And if the tax reporting team is interested in that, because tax needs to be reported, they subscribe to that event, and then they do whatever they need to source or do next, synchronously. It can be REST after that, it can be MQ after that. But in the middle of the development, it's the single event that an order was created in the organization. So there may be a shipping service that also subscribes to that information to check if it's in stock and they need to ship it to a customer. There may be a reporting service to understand which product is the most popular in my web shop. There may be hundreds of services being interested in that single event, and it's a lot more reactive way of coding. It's a lot more event-based than the previous paradigm, when you just call, for example, in REST, you just make a call, you receive your response, and then you move on with the data. For example, that response will be the input into your next function. So this is a bit of a different paradigm. So as we all shifted our paradigm, and we are all convinced that we need to use this, and at least we need to give it a try, why would you do this with Confluent? So first of all, we increase developer velocity in multiple ways. We've got Confluent Cloud, which is a fully managed SaaS service. So you don't really need to care about the infrastructure anymore, like managing Kafka, running Kafka brokers and zookeepers, and taking care of application factors. It's not an easy task. You might not want to do that. You might want to actually focus on the development itself. Like, what is the code? What is the functionality that you're trying to achieve in your organization? Then we've got Schema Registry. We are really proud of this because it helps you to provide data governance. So the Schema Registry enables you to provide a contract in between your clients subscribing to your topics and clients who are producing the topics. So if you want to jeopardize that, you want to send a message that doesn't align with the schema, then what happens is that your message gets into a dead letter queue because it doesn't align with the schema. So you can't break other consumers, all those thousands of services subscribing to your topics in real time. So that's quite cool. And then we've got KSQLDB, which is a real-time analytics, SQL semantic software that we provide. So you can write SQL, basically, on topics in real time. You can join them in real time. You can do fraud detection. You can do windowing. It's not exactly ANSI SQL, as you would expect, because it's done on topics. It's not really done on a database. But there are a number of use cases. And I think the most powerful one, we usually don't mention this, is that very often with the filtering capabilities, with simple capabilities, you can spare a few microservices. So KSQLDB does the filtering for you instead of your client doing it at the very end. We also build highly reliable and fault-tolerant microservices. So we provide infinite storage, we have multi-region clusters for production use cases, and we have end-to-end stream governance. So if you wanted to go back in time and you wanted to see who was producing into your application, you're doing a post-mortem call or something like that, then you can see what was going on 5 days ago, who was producing, who was subscribing, and what happened in your applications. So we have 120 plus connectors that enable this integration. And we always talk about them because there are a few of them that you can run in the cloud. There are a few of them you need to run yourself. But I think one of the most important things is you don't need to write them on your own. So you're not adding to the tech stack again. It's not something you need to maintain all the time. All you have to make sure of is that you do the right configuration. That's really important. But The connectors enable you to not add more technical debt to your organization if you're developing software. We've got cluster linking as well for data recovery use cases and committer-driven expertise. So Confluent was funded by the original creators of Apache Kafka. So we know Kafka inside out, I would say. Jay says he doesn't write too much code anymore, but I bet he still knows it. So I thought I would put down a few common scenarios that we see. So we have the CDC from legacy database systems. So CDC stands for Change Data Capture. So whatever gets inserted, updated, or deleted into a database, you can check and just drop it into a topic, and then you can process it real time. I will talk about that, like why this is so powerful and what is the architecture we usually propose. Then we also have queries from big retailers to modernize legacy systems. I have seen IBM MQ used at various places. We can also channel the queue into a topic, making sure that you become more cloud native and you can modernize your systems. Then we can enrich events with less code using stream processing. This is something I mentioned about KSQL DB, but if you're into Java, you can also use the KStreams API. Both of them are completely open source, and you can do real-time filtering, joins, mappings on topics. And there is ensuring data compatibility. As I mentioned, your services can rely on the schema registry as you have a rigid structure that you expect every message to have. So the Strangler fig pattern. So someone told me I should put a picture about this because it's a plant. And my manager told me he didn't know it was a plant. So it's a really special plant that goes up onto a tree and it starts growing onto the tree, and then it starts strangling it once it's strong enough. So it kills the tree, actually. And this is a pattern we often talk about when we talk about mainframe modernization or migrating to the cloud, for example. So as I mentioned, this is where we often start with. We have a monolithic approach, a catalog service, an order service, and a payment service. And there is a load balancer. I call it load balancer here, but it can be any facade, something that abstracts what's going on in the backend when you make a request to a service. And then you have a client and web application. And if you work with Django, for example, WordPress, I'm pretty sure that you know that this is what comes out of the box. So with WordPress, I think it comes with MySQL. With Django, you can choose whatever you want. And I think Flask is pretty similar to this one as well. So what we usually recommend is that you move in an incremental way. So first, you have an endpoint for the reads, and you put a change data capture connector connected to your database. The change data capture will record all the inserts, deletes, updates from the database, and it will just all load them into a topic. So instead of going into the database, when you request information, you go to this topic, which is a cloud-native microservice. You may even start using different sort of technologies. You can sync it into MongoDB if that's your preferred choice. You don't necessarily need to go into the topic, but the topic enables you to offload it into third-party applications that you haven't been able to do before. Now, one thing to mention that this works really well if you don't change the structure of your data. If you do, it may become a bit more difficult to test this out. But here now you sort of moved half of the functionality of your mainframe, your main database, into something else. So you also scaled up your service a little because you don't always have to go to the database for all these reads. Cool. Now, the next step is, after you test it out, that all the reads are working from this cloud-native microservice, is that you put the writes as well on this microservice. So every time, let's say, a customer registers to your online shop, that registration would also go into this catalog microservice, into a topic, and this new user would be first recorded there, and then it would be synced back to the database. The reason you still sync back to the database is because the database is part of a very interconnected system. There is the payment service, the order service that still remain there, and they're going to be looking for those items. They don't know that you're migrating off some of your workloads. So you have this parallel sort of universe where you have a microservice in the cloud, hopefully, recording all the writes and the reads coming from your application. You're still syncing back into the monolithic application just to make sure that everything that's relying on that information will not break. But you have already, you were able to move at least one of the functionalities off from the mainframe. And you can do this incrementally, one by one, until the point you strangle the application completely, if that's something that you want to do. Lastly, what I wanted to mention is that there are third-party applications such as Elastic, Amazon S3, MongoDB. Anyone in your organization can come and see that data instead of querying the database. So it's not only about the fact that you move the functionality off. It's also that if text reporting service needs to know about this, they can subscribe to the topic instead of going to the database as they used to do that before. So strangling the database and strangling the mainframe. I think this is what I'm going to close with. And I thank you for your attention. It's been a pleasure to present here. And my name is Semjen. I'm a solution engineer at Confluent. This is my email address if you wanted to reach out to me. And we are right in the middle at that booth. So if you've got any questions, I'm happy to answer them at the booth. I'm going to be around for another 60 minutes or so.